In this third part of this topic, we are going to study a few more mechanical features of the OLS multiple regression. These are features that are always true and that therefore are mechanical, so they come under the umbrella of the description of OLS, but they are a bit more subtle, so we decided to split this video, put it separately. The first issue is that multiple regression uses variation that is uncorrelated with the controls. Okay, so we have I have written the standard population model that we had for simple regression, where y depends on x, and there is also an error term, epsilon, and so on. In this case, I'm writing not just x, but I'm going to write it as x1, okay? This is important because there will be an x2 that comes later. So y depends on x1, there's an error term, beta naught, beta 1, these are the standard parameters of the intercept and the slope and so on. But we said that there are cases in which the error term contains another variable. In the case of the effect of competition on prices, that was distance. In the study of number of daughters on voting, that was number of children. That is there in the error term and is creating a bias, or it is not allowing us to obtain unbiased estimates because it is correlated with x1. So remember, we justified the need for multiple regression from the fact that x1, which is our main independent variable of interest, and x2, which, in simple regression is in the error term, are correlated with each other. But now imagine that we could take x1. We will see that we can do that later, in practice. But imagine just conceptually. Imagine that we could take x1 and split it into two parts, decompose it into two parts, divide it into two parts. The first part is x1, and that is the part that is correlated with x2. But there is a second part. Still, that part is, a component of x1, but that second part is not correlated at all with x2. Well, then, if we had a simple regression of y on that second part of x1 that is uncorrelated with x2, we will be obtaining an unbiased estimator, an unbiased estimate. We will not need to control for x2 because there will be no correlation between x1 and x2, which is in the error term. That is, assumption 5 will hold, we will have unbiased estimates. Well, it turns out that in practice, we can actually do that. We can actually decompose x1 into these two parts. And we can do that in practice, statistically, econometrically, by running a regression of x1 on x2. Let's see just a repetition of how this works. Imagine the following strategy, therefore. We run an OLS regression on this multiple regression model. Our objective is to study the effect of x1 on y, but it is a multiple regression model in which we explicitly account for x2. We control for x2. Control for x2. Imagine instead that we follow this other route, this other avenue, this other way of getting the estimates, this other strategy. We start by running an OLS regression on the following population model. x1 here is the dependent variable, whereas x2 is the independent variable. Okay? Now, this OLS regression, you may think is a little bit funny. Okay, we are regressing one x on the other x. But just bear with me. Imagine that we run this OLS regression. The population model is the one that you are seeing there. x1 is equal to some intercept. Now we are calling this intercept alpha 0, plus some other intercept, which we are calling alpha 2, x2 plus some error term, which we are calling upsilon. Okay, this v in there that is in red. So in this model, we have that x1 depends on x2 and some error term. Now, after we have run this regression of x1 on x2, we will have certain estimates. Alpha naught hat, alpha 2 hat, and so on and so forth. On the basis of these estimates, we could compute the fitted values. We will write the fitted values as x1 hat. On the basis of these fitted values, we could also compute the residuals. The residual will be x1 minus x1 hat, and we will write these residuals as being upsilon hat, the same way that in the previous topic we're referring to the residuals as epsilon hat, because in that case the error term we're calling epsilon instead of upsilon. Now remember, and this is critical, a mechanical property of a regression, mechanical property number 2 of any regression, of any OLS estimator, is that the residuals are uncorrelated with the independent variable of interest. Let me go back here and show you. Here it is. Mechanical property number 2. For every regression, multiple regression or simple regression, it doesn't matter. Mechanical property number 2, the residuals, in this case it is here written epsilon hat, but in the equation that we have later is upsilon hat, are uncorrelated with the excess. In the case of the regression that we're interested in, these x's are x2. Okay, so the residuals are the part of x1 that is uncorrelated with x2. Notice that we have accomplished the trick that we were thinking about earlier. We have decomposed x2 into two parts. The first one is the fitted values, x1 hat correlated with x2. The second is the residuals, upsilon hat uncorrelated with x2. If now we take a regression, we write a population model of y on upsilon hat, which remember is the part of x1 that is uncorrelated with x2, then we will get, in this population model, we have that the slope is gamma 1, we will get a different estimate, gamma 1 hat. Well, it turns out it is a result that the first strategy, where we run a regression on x1 and control for x2, will give us exactly the same estimate as the second strategy, in which we take x1, decompose it into two parts, run a regression of y on the part of x1 that is not correlated with x2. That is, beta 1 hat from the first strategy is always equal to gamma 1 hat from the second strategy. So this is a result. In other words, essentially what I just told you here. We get the same estimated effect if we regress y on x1 and x2, then if we regress x1 on x2, get the residuals from there, and regress y on the residuals. An example of this: are prices higher in less competitive routes holding distance constant? In a multiple regression, we could get the estimates that I have shown you earlier. You may remember this minus 0.080, okay, from previous slides. But we could also run a regression of competition on distance of the x1 on the x2. This will be the OLS regression line. You can see the fitted values of competition are equal to minus 1.7 plus 0.525 distance. Okay? On the basis of this, we could compute the residuals arising from this regression. The residuals will be the values of competition minus the fitted values of competition. We could then run a regression of the y variable fares on these residuals, and in that case we will find exactly the same as earlier. Okay, now let's talk about the goodness of fit. The goodness of fit is a concept, okay, or a magnitude that we can calculate on the basis of a multiple regression that is done in exactly the same way as we did it with the simple regression. That is, we define the total sum of squares, explain sum of squares, residual sum of squares in exactly the same way as we had earlier, and it can also be shown that the following decomposition is true. The total sum of squares is equal to the explained sum of squares plus the residual sum of squares. Then we can define the goodness of fit, or R squared, of a regression as the ratio between the explained sum of squares and the total sum of squares. This is capturing the percentage of the variation in the y. You can see at the top, total sum of squares, the variation in the y, how much y deviates from its own mean, that is explained by the y hat, that is explained by the independent variables that we had in our model together with the regression that we have run. One reason that we are mentioning the goodness of fit in this other topic on multiple regression is to illustrate certain facts about the R squared. And these facts are that every time that we include a new variable in a regression, say when we have x1 and we add x2, or when we had x1 and x2 and we add x3, whatever, we can explain y a little bit better. Okay, because we have more variables that potentially can allow us to predict the value of y better. This will imply that the explained sum of squares will increase, and also that the goodness of fit, the R squared, will also increase. Now, one thing just to remember, okay, the goodness of fit is a concept that is somewhat orthogonal and related to whether the estimates are unbiased or not. It is a mechanical concept. We may be able to explain mechanically a lot, but still not have unbiased estimates. We're going to get unbiased estimates depending on whether assumption 5 is satisfied or not. Okay, and that depends on a completely separate type of issues as the goodness of fit. We are now going to provide a simple rule to understand the difference in the estimates that we obtain for the effect of a particular variable on another variable using simple and multiple regression. To start thinking about this difference, or the rule that captures this difference, remember that in the study of the effect of having a daughter on the political voting records of US congressmen, we had concluded that the simple and multiple regression models gave us very different estimates. We have them here in this slide. In the simple or single regression model, we had that an additional daughter decreased the liberal voting record of that congressman by 2.14 points. If instead in multiple regression we study the same effect of daughters on liberal voting record, but this time controlling for the number of children, in that case we obtained a positive effect of daughters on the liberal voting record of 5.44. Just to recap in terms of this comparison, remember that we said that if in the multiple regression model assumption 5 holds, and assumption 5 is that the error term of this model, in this case upsilon, is uncorrelated with the independent variables of interest, if that holds, then this 5.44 is an unbiased estimate of the effect of daughters on the voting record of this gamma 1. Okay, but this means that the bias of the simple regression was quite large. That is, we obtained a minus 2.14, and we should have obtained, if we had run a regression that provided us with unbiased estimates, we should have obtained 5.44. The difference, minus 2.14, and the difference of that with respect to 5.44, as you can see there at the bottom of this slide, the difference, this minus 7.58, is the bias that is associated with this simple regression model. Okay? By the bias, we mean how much the simple regression model was getting it wrong on average. It was giving us an answer of minus 2.14. It should have given us an answer. It should have given us a guess or an estimate of plus 5.44. The difference is what we call the bias. Okay? The difference between what we had got in a model in which we were not obtaining unbiased estimates and we should have got in a model that provided us with unbiased estimates. Okay, so we write it there. The bias associated with simple regression, how much we got it wrong, is minus 7.58. Remember also that the effect of the number of children on the liberal voting record was minus 7.11. Let's go back here and see that. You can see that in the multiple regression model, the effect of the variable, okay, that we were controlling for is minus 7.11. So we have it here in green. The next thing that we can do is to run a regression that captures the relation between the variable that we have to control for, children, and the independent variable of interest in our model, which is daughters. Daughters is the variable whose effect we want to get an estimate of. If we run this regression, okay, if we run a regression of children on daughters, say using a population model such as the one that you can see there, we will obtain, and in fact, I have done that in practice, okay, that the estimate associated with that simple regression is 1.07. Okay, you can see that estimate is alpha 1 hat, okay, the estimate of the relation alpha 1 that, as you can see in that population model, is linking the number of daughters with the number of children. So just to recap once again, the bias is minus 7.58. The multiple regression coefficient of children is minus 7.11. The estimate or the coefficient of the relation between daughters and children is 1.07. Well, it turns out, you can do this very easily with a calculator or by hand, that minus 7.11 times 1.07 is equal to minus 7.58. In other words, these two effects, the effect that we're calling there the gamma 2 and the effect that we're calling there the alpha 1, multiplied by each other, are equal to the size of the bias, which is the difference between what we should have obtained by using an unbiased estimation in which we control for children and what we obtain with simple regression. In other words, the bias, the difference, okay, between these two coefficients is equal to the product of these two things. Formally, think about these three models, these three population models. The first one is the population model associated with simple regression, okay, that captures only the effect of x1 on y, but without explicitly controlling for anything. The second, as you can see in the second equation in there, is a population model devoted to capturing the same relation, but this time controlling for some additional variable x2. The third model is a mechanical model that is capturing the relation between x2 and x1. As we showed earlier with this example, the difference between the simple regression coefficient, that is beta 1 hat, and the multiple regression coefficient, gamma 1 hat, is equal to this product that you can see in there, gamma 2 times alpha 1. as you can see in the equations, gamma 2 is the effect of x2 on y, and alpha 1 is the effect of the relation between x1 and x2. Note that these two coefficients are going to be equal to each other, and the bias is equal to 0 when the simple regression model, the first population model that we have up there at the top, gives us unbiased estimates. We know from topic 2 that it gives us unbiased estimates when assumption 5 is satisfied in that population model. The condition for assumption 5 to be satisfied is the one that you have there, which is that the expectation of the error term is always the same regardless of the value of x1, or in other words, the error term and x1 are not correlated with each other. Well, when will that happen? The equation, the equality that we have in there that captures the bias is telling us when that is happening. You can see that from that equation, this equation here at the bottom, beta 1 minus gamma 1 is equal to this product. From that equation, we have that beta 1 will be equal to gamma 1 when either of the things to the right is equal to 0. For instance, when gamma 2 is equal to 0. When will gamma 2 be equal to 0? In the second equation at the top of this slide, starting from the top of this slide, we can see that gamma 2 is equal to 0 when x2 does not affect y at all. If it does not affect y at all, then x2 should not be in epsilon. That is, it shouldn't be part of other things that are not x1 and affect y. The second reason as to why the bias may be 0 and gamma 1 is equal to beta 1 is now looking at the second element in the product at the right at this bottom equation when alpha 1 is equal to 0. When will that happen? It will happen when x2 and x1 are uncorrelated with each other. That is, maybe x2 is one of the things that affects y, but it is not correlated with x1, and therefore epsilon and x1 are not correlated with each other. Assumption 5 still holds in simple regression. So just, again, we remember this is a simple regression coefficient. We can bring the, way of disentangling the bias into this figure that we have been showing throughout in order to understand what omitted variable bias is. In this figure, we have that our interest is in the effect of daughters on liberal voting, and the true effect let me just go back here. The true effect if the multiple regression model is unbiased, okay, is 5.44. Okay, so just go back here. You can see that, okay, the arrow that goes from daughters to liberal voting is capturing the partial true effect, and that is 5.44. However, in simple regression, there is an indirect effect. There is something in the error term, which is children, that is also correlated with daughters. You can see that there is an arrow capturing the relation between children and liberal voting. There is this arrow because children is one of the variables in epsilon which affects liberal voting, and the multiple regression coefficient is telling us that an increase in children decreases liberal voting by 7.11. On the other hand, there is also a relation between daughters and children. The population model linking x2 with x1, when applied to x2 being children and x1 being daughters, tells us that an increase in the number of daughters increases the number of children in expectation by 1.07. Well, this indirect effect that you can see there from daughters to children and from children to liberal voting is giving us is the same as the bias. Okay, and this indirect effect is, well, by how much does it increase the number of children when I increase the number of daughters, and that is 1.07, and by how much does liberal voting increase when I increase the number of children, and that is by minus 7.11. So the bias is the product of these two red arrows that you can see in there. So again, another variation of this idea is that sometimes with simple regression, we know that this simple regression is not unbiased. That is, it is not providing us with unbiased estimates. Our estimates are likely to be unbiased. Okay, but we don't know, maybe we don't have this other additional variable that we need to control for. In these situations, it is very useful if we can at least give a sign to that bias. That is, we can say whether it is positive or negative. Again, we start from the wrong or biased model. The true model, or the model that will be providing us with unbiased estimates, will be the one in which we control for x2. Okay, and notice that there I am highlighting the effect of x2 on y, this gamma 2. We could also run a regression of x2 on x1. Again, I'm highlighting the effect of x1 on x2, which is alpha 1. We can give a sign to this bias, because the bias is the product of gamma 2 and alpha 1. When both of them are positive, then the bias will be positive. When both of them are negative, as we can see in this table in the bottom right cell, both of them will be positive. If one of them is positive and the other is negative, then the bias will be negative.